Okay, so it's time for the last talk after the session. Let me introduce Guodong Pang from Rice University. He's going to talk about stochastic PDE and epidemic models with very important infection agent. That's
oh, please. Thank you. Thank you for the opportunity to speak at the workshop. This is a joint work with Etienne Pardoux, during the pandemic, a lot of us probably have heard of this compartment models, ODE, PDE models, and so we have taken a individual-based approach. So start from stochastic individual-based model, and then prove skinny limits and establish the PDE and SPDE limits. So today we'll focus on the SPDEs. So here's the outline of my talk. So I'll start with some, because I'm not sure everyone has the same background. So I'll briefly talk about the standard epidemic models, and then I'll introduce the new epidemic models with varying infectivity and infection age-dependent infectivity, and then get to the PDE and SPDE models as the scaling limits of the measurement processes. Hope you're not disappointed that don't see SPDE in the first slide. So and then I'll conclude in the end, right? So the standard epidemic model. So we consider a homogeneous population, so well mixed. So suppose they're individuals. They are initially either susceptible, infectious, or recovered, or removed. So each individual has contacts with other individuals in the population at some random time. And each infected individual remains infectious for some random duration. When an infectious individual has contact, it picks another individual uniform at random and tries to infect this individual. And if the latter if the individual is susceptible, then it becomes infectious and can affect other individuals. Otherwise, nothing will happen. So at the end of infection duration, each infected individual becomes recovered, and so can no longer be infected. So this is the standard SR model. So in the homogeneous population. So the dynamics of the model can be described using the three processes. SIR, we index by n because we consider the large population limit, so let n population size go to infinity. So the sum of the three is equal to the total population size. So essentially just two processes. The standard model has a constant infection rate. We use lambda for that. And so if the infection duration has exponential distribution, then the process is Markov, right? So then dynamics can be described using the rate 1 Poisson processes. So the infection rate, so the infection rate is just lambda, the infection, lambda times IS over n, right? So that's the instantaneous infection rate in the population. And and this time change Poisson process, we can also use Poisson random measure, because working with the Etienne, I've learned to use more Poisson random measures to derive to formulate the processes. Okay, so we can use this using Poisson random measure. Then if the Q is the standard Poisson random measure, and this will be the intensity process for the process. Okay. So if you look at, because we let population size go to infinity, so for a large number, we scale down the processes by the population size n, and so then we will get this standard compartment model, the ODE models, right? So this S is just the decrease in function with this rate lambda times I S, and I is the infection rate minus the recovery rate. Okay, so this is the very standard the ODE model. And for the CLT scale processes, we'll get the diffusions in the limit, and essentially the centered Brownian Poisson process will converge to the Brownian motion. So that's what we get. So because we focus on the SPDEs, I'll skip this part, and we'll. Okay, so in this standard model, if the infection duration is general, then we have a non-Markovian model. So if I let F to be the distribution of infection duration, and F0 is the distribution function for the remaining infection period for the initially infected individuals, then we get, instead of ODEs, we get the system of integral equations, right? So, and if you look at this infection population size, this just basically the initial times the probability that those initially infected are still still infected at time t, right? So here, this is if at time s is the infected, and this is the infection rate, and this is the probability that is still infected at time t. So for the CLT limit, we get a Gaussian-driven type of stochastic Walterian integral equations in the limit. Okay. Okay, so here's a plot to show the difference between the OD and the integral equations. So the left figure, is the Markovian, the OD dynamics, and using and right figure is is non-Markovian, the integral equation solutions. We choose we choose the distributions, gamma distribution, choose the parameters so that the means the same. So so now you see, for these two type of distributions, the non-Markovian model, right? So the integral equations actually has a higher peak for the infection, and it takes a longer time to recover. To further illustrate this, so if you look at suppose the contact rate drops all of a sudden at some time when the pandemic is growing, for example, because of lockdown measures, and then we'll compare these two models. The OD model, we always underestimate infections. Okay, so there's reason to believe that we should use a much more general model than just the ODE compartment model to study the pandemics, to predict the pandemic. Okay. Well, because I think it's though the integral equations, it captures uses all the information from the distribution, right? So if there's more variabilities from the distribution, then it captures in the equation. So well, the ODE is only the one parameter, just the rate. Yeah. Well, we didn't prove it. I think perhaps one can prove it. Yeah. So. Dotted blue is the non-Markovian model. The orange is the okay. Blue is the Markovian, non-Markovian is the above. Yeah. Yeah. Okay, so in the standard models, people, we have used the constant infection rate, right? So during the pandemic, we have seen this article on Nature Medicine. So basically, the infectivity of each individual is not really a constant. It changes over time. It first increases, then decreases. So in this article, they showed from Wuhan, I think. So the viral loads for different individuals from the days after the symptom onset and different shapes of the viral load. Okay, so motivated by this, we model each individual, the infectivity level, using a random infectivity function lambda t of this shape. So basically, it can have a 0 period for exposed, and then increase and then decrease back to 0. Okay. So, and then this random function can also induces the infection duration. Okay, and it actually can include both the exposed and infectious periods. Okay, so to study this process, this model, we have to introduce another process. It's called the total false infection. So this is basically the total false infection at time t for the initially infected individuals, and this is for the newly infected individuals at time t infection, the infectivity level. Okay, so this is the aggregate level of all the infected individuals. So this actually can be tested from data. So I've been talking with the UT Health department. They actually they have samples from wastewaters, and from wastewater, over time they have these the viral load levels, right? So by multiple, and this is basically given by this process. Okay. So adding this process to the dynamics, so then we first actually have these two processes: the susceptible individual population and the force of infectivity. So these two solves this set of integral equations. Okay. So now I have if you notice that I have labeled here in red the false infection. In the standard model, this is just lambda times I, right? So here is changed to be a general function, force of infection. Okay, so once we solve this set of equations, then we can get to this the size of infected population. Yep. So this is not a infection age dependent infectivity yet, because we assume that at time 0 you have profile may have started at some time before, right? So that just yeah, whatever you want. Yeah, exactly. It just because it start from 0 and then to t, right? So yeah.
Whatever initial conditions that we have, plus how fast the develops.
Yes. So for that, so here we assume their ID, right? So just okay, you start from 0, it can be anywhere. So and then just the average, that's the mean of infection at time t for initially infected. Okay. Yeah. Yeah. Yeah, exactly. So this is a plot of if we study this new process, so we get to this. The top figure is the false infection. So for this figure, we simulate this model. We use the triangle type of infectivity function, randomized, and then we got this shape. Okay, so this is actually mimics a lot of the reality, and so then the other curves look quite similar. So, okay, so this basically a couple remarks. So if lambda t is just simply a constant times indicator t is less than the infection duration, that reduces to the standard model. And then there's a concept of the basic reproduction number or not, right? So by definition, it means the average number of individuals infected by infectious individual in large fully susceptible population, right? So in the standard SRR model, this is lambda times the mean infection duration. For this general model, it's just it becomes integral of the mean infectivity level over time. Okay, so that's the O area of the curve. Okay, and this also extends to SIS, SRS models. Okay, so now we get to the where we get the SPDE limits. So we consider a more detailed model. So we use a measure valued process. We track the age of infection for each individual. So we use this measure value process mu and t. Okay, so that's basically looking at the distribution of each time t infected individuals, their distributions over the infection ages. Okay, so we let a time. Okay, for initially infected individuals, we let tau Jn0 tilde this and eta J0 to be the infection age and the remaining infection duration for the initially infected individuals. And tau in and eta I be the infection time and infection duration for the newly infected individuals. So the first term in the measure value process, this first term is basically look at the distribution of the infection ages for the initially infected individuals at time t, and then the second term looks at the newly infected individuals. Okay, and the infection process in t just the intensity is S times this F, the forced infection. Now the forced infection is changed a bit slightly from the previous slides. So here, because it's infection age dependent infectivity, so we assume that they all have the same profiles, and at time 0, at time t, basically we track, okay, this is like how long before they were infected before time 0, right? So that's the age at time 0. Infection age time 0. So this is the total force of infection for this infection age dependent infectivity model. Okay, so this is this would describe the dynamics, right? So it's rather complicated because they all kind of depend on each other, right? So how to analyze this? Well, we came up with this expression, the evolution dynamics using 2 Poisson measures. Okay, so this is the regional measure value process. So this is the evolution dynamics. In evolution dynamics, we use 2 Poisson measures. So this is for infection. This is just for describing the infection process, nothing really mysterious. But the second term is tricky. Okay, this first term is just describes the evolution of ages for initially infected individuals, and this term is for the it's a recovery process. Okay, recovery process. We have to introduce this new function, a function h, which is the inverse of the distribution function of the normalized the hazard rate biased measure. Okay, so we let h to be the hazard rate function for the infection duration, and defining this h function, what does it do for us? It identifies which individual will recover next, right? So among all the infected individuals, which one will recover next? So this is what it does, this function. Okay, so with this, so this term will describe the recovery process. Okay, so if we're given the infection in intensity, then this is almost like an infinite dimensional birth death process. It's a very very clean, and it helps a lot to analyze the measure value process. Okay. It describes the stochastic flow using input and output processes. Okay, this is the most crucial thing for this talk. Okay, so and then with this, right? So now, if you look at the large number scale process, again, so all divided by n, everything divided by n. So what we have is, and then we use the centered, the compensated post-random measures. Okay, and then this will be what comes into basically the drift. Okay, this is the deterministic flow essentially, right? So for all large number limits, and then all of these will converge to 0, and then this will give me the PD limit. Okay. All right. So here's the PD. It's quite it turned out to be simple. It's a linear PDE. We have to assume that to prove the convergence, we have to assume that the Hazer ray function is bounded. And then for this PDE, we are able to write down, we can show the solution is unique, and we are able to write down the solution explicitly. It's given by this formula. Okay, so the first term essentially is the for the newly infected individuals, dynamics for the newly infected. And then the second term is for the initially infected. Okay. And then inside this, so there's this Wuppertal bar, which is solution to use the solution S and F is solution to this linear integral equation as input. Okay. So, all right. So getting to the PDE. So basically, it's just the first line. Remove the ends, right? So and I take derivative with respect to t, and then we'll get we'll partial derivative with respect to t. We'll get the PDE right away. Okay. So what about the SPDE? So the SPDE. So what we do is we consider this CLT scale process. We center around the limit. So under some mild regularity conditions, the conditions, okay, we also assume the Hazer ray function is bounded, but also some regular conditions on the lambda functions. Okay, so and then we get this is the PDE. It's SPDE. So it's also a linear it's a linear process, right? So there are two white noises. So WINF is a standard. So this is for infection process. It's the standard Gaussian white noise. This WREC for recovery, and that's the a centered Gaussian white noise with this covariance structure. And then there's this Wuppertal hat process, which I will talk about next, right? So essentially, right? So this is almost like the linear the PDE, but we're adding the noises to it. Okay, and the noises to it. So, well, it could be. It's yeah. So thanks. And okay, so for this linear SPDE, we can also solve it explicitly, actually. So it's similar to the linear to the PDE. So this is the solution. So we can this is for the initial randomness and for initially infected individuals. And then this is for infection process, this recovery process. Okay, then together with this hat, Upsilon hat process in it. Okay. Okay, so that's the SPDE. It turned out to be simpler than we expected, right? So then, but it's a lot of work to get to this point. But I think it's interesting finding that that for this complicated model, we have this linear SPDE and the noises. Okay, next I'm going to talk about the noises and also the Upsilon hat, right, process that kind of complicates the problem. So we have seen okay, WINF, which is the infection white noise, right? So this is recovery white noise, and the mu hat 0, what is it? So mu hat 0. So this comes from we make assumption on the infection age for the initial infection individuals, and we assume that they are ID, have a common law, so that this will converge to a Brownian bridge, a time change Brownian bridge. So then this first term here in solution to the SPDE is just integral with respect to a Brownian bridge with time change in there, right? So this is the first term, right? So this is independent of the W and the two white noises, okay? And then what is the Upsilon hat? Okay, Upsilon hat is a little bit complicated, right? So it's okay, it's a linear combination of the S hat and F hat. It's a susceptible process and also the force of infection process. And these two actually are a system of linear equations driven by Gaussian noises. Okay, and the Gaussian noises, one of these is from the initial quantities, right? So and okay, two of these, the ones, the S hat 1 and F hat 1, these are from the infection white noise. So there are two, the F2, F02 and F2, these come from the randomness from the random infectivity functions. Okay, so this basically captures the in the formula just the covariance functions of the lambda functions. Okay, so in the special case, if we assume that the lambda t is a random, but the lambda t is just a determinant function times indicator function that t is less than the infection duration. In that case, those two, the last two they will vanish, and then we only have the initial randomness and the two white noise. Okay. So it becomes simpler in that case. And okay, you may ask, okay, well, I never mentioned about being Markov, right? So if you want to use a measure value process, we track everything, and we should get the Markov process. But we don't get Markov process because of the random functions. If we in that special case, and then we do have a Markov process in the upper limit and also the limit. Okay. Okay, the proof of this actually, okay, maybe I'll use 1 minute, no time. Okay, well, just basically we use the properties from stochastic integral with respect to post-random measures. So we have looked at models, not just SRR, we look at models with varying infectivity and the winning immunity. Basically, this is SRS model. So in standard models, once individuals recover, they lose immunity immediately, but that's not realistic. So there's a gradual loss of immunity. So then each individual goes over the cycles, like infection and recover and loss of immunity and then get infected, right? So then they use this cycle, right? So we have established PDE limits, large number limits for this model. Helen has talked about it, I think a week ago in the seminar. So So for this model, I think it's also interesting to study the SPD limit. For that model, it's there are some interesting features like, okay, so there's equilibrium point, convergence to stationarity, and what is the invariant measure for the SPDE and so on. So and there's a lot of interesting questions to study. And then there's also spatial models. So we want to capture the models I talked about so far. These are homogeneous models. There are also models with spatial heterogeneity and population heterogeneity. So we want to capture these heterogeneous features. So one way to look at spatial heterogeneity is to look at a multi-patch model. And you can have a fixed multi-patch, number of patches fixed, but also number of patches go to infinity, the spatially extended. Then we have a paper established the PD limit for that model. And one can also look at a model on random graphs. So basically, each individual is node graph, and then the connectivity change over time and random connectivity. So and also be interesting to look at this type of models for these systems. Okay, and some references. And the SPD paper should be ready soon. I hope so. And well, thank you.
Right.
Yeah, it's a complete graph. Yeah. Mm-hmm. Yeah, yeah. Uh-huh. That's okay. Yeah, yeah, exactly. Yes, exactly. Yeah. Right, right. Yeah. Yeah, that's different too. So far, we have just kind of more dense type of models, right? So then we get the spatially dense model. We get a PDE on graphons, basically, right? So that's when we haven't looked into like a sparse type of models. Yeah, and also we organized a workshop on spatial epidemic models in Paris in May. So we had the conference website still there. So we'd have talks about two-layer networks and many interesting aspects of spatial epidemic models. Okay. Yeah.
What's the main tool that you use?
Stochastic properties of stochastic integral with respect to surrounding measures and tightness. Tightness is a bit hard for this, especially for the recovery process. That part is a bit challenging to prove. So we use a lot of surrounding measures, properties of surrounding measures. So yeah. Of similar, quite similar. Some. Mm-hmm. Yeah, exactly. Yeah, yeah.
Okay, if there's no more question, then thank you. Okay.
Well, thank you.